I now call to order the Society's 2,399th meeting in the 148th year since its founding in 1871. Good evening, everyone. Good evening. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., dedicated to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Steve Squyres in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. We will begin with a reading of the minutes of the 2,398th meeting and the lecture by Charles Norton on CubeSats. We will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. Please join me in thanking the sponsors of the 2018-2019 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous sponsor who's asked to remain anonymous. I am pleased to announce that the following new members have been elected to the Society. Carrie Welsh, a medical officer with FDA, particularly interested in clinical chemistry, epidemiology, and regulatory affairs, who learned of PSW through Meetup. And Omobola Cole, a business analyst broadly interested in science, who learned of PSW from one of her professors in the biotechnology program at Georgetown University. And tonight's speaker, Steve Squyres, whose background and interests will be clear to you, at least in part, from tonight's proceedings. Please join me in welcoming them to membership. For our new members, we have a signed reprint of Volume 1 of the PSW Bulletin. And if you want to pick up your copy, please see me after the lecture. Recording Secretary James Heelan will now read the minutes of the 2,398th meeting and the lecture by Charles Norton on CubeSats, delivered here on October 19th.
Thanks, Larry. Good evening. On October 19th, 2018, President Larry Milstein called the 2,398th meeting of the Society to order at 8:04 p.m. at the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, Charles Norton, Special Advisor for Small Spacecraft Missions at NASA. His lecture was titled CubeSats, A Giant Revolution in Space. Fully functional satellites have gotten smaller and less expensive to both produce and to launch. Norton showed the Society a model of a 10 by 10 by 30 centimeter hyperangular rainbow polarimeter called HARP that NASA intends to launch from the International Space Station in November 2018. Its mission will be to measure the Earth's cloud and aerosol properties. The small satellite will carry communication antennae, solar panels, a fisheye lens with imaging electronics within the system, an attitude determination and control system, GPS, and other software. Norton said, smaller, less expensive satellites will enable scientists to take greater risks in exploring space. For example, the Cassini mission to Saturn revealed a previously unknown radiation belt and complex organics in the planet's rings. Instead of sending another Cassini-sized mission to analyze these discoveries, NASA could instead send small satellites into the hazardous environment. Norton posited that scientists could similarly leverage the economics of small satellites to monitor individual exoplanets discovered by the Kepler mission. Currently, small satellites are being used to collect large data sets. For example, NISAR is a joint NASA and Indian Space Research Organization mission collecting 85 terabytes of data daily, monitoring the Earth's ice mass change and other complex processes. Norton said the efficiency of small modern satellite technology and the abundance of data waiting to be gathered makes space science more accessible to smaller scientific organizations. To that end, scientists have developed CubeSats, which utilize a standard form factor and the 10 by 10 by 10 centimeter units integrated into a containerized container that actually was on his slide. It was on the slide, called a P-pod. The P-pod piggybacks onto a larger mission as a secondary payload to release CubeSats at their intended destination in space. Norton said there is little to distinguish the capabilities of large bus-sized satellites and CubeSats. For example, RainCube, a precipitation radar CubeSat, carries a deployable mission antenna to measure precipitation. RainCube has a precipitation radar, solar panels, multiple radios, GPS, battery modules, command and data handling systems, and thermal control systems. And unlike large craft, Norton said, CubeSats can be quickly replaced, allowing missions to survive failures that would otherwise derail those dependent on bigger, more expensive equipment. CubeSats may also support larger missions. For example, the Marco mission is 2 CubeSats currently on their way to Mars with NASA's InSight lander. Marco will deploy and rendezvous to form a bent pipe relay to capture the entry, descent, and landing signal from the InSight lander and relay it to Earth. Norton believes CubeSats will revolutionize space exploration. He described the lunar flashlight mission that will use lasers to explore the moon for water, ice, and other volatiles. MINX is a solar spectrometer making measurements of photon energy associated with coronal mass ejections. IceCube is an imaging radiometer satellite measuring cloud ice particles. Cygnus uses GPS reflectometry to improve hurricane intensity models and to measure near-surface soil moisture. CubeSats have also recently observed Hurricane Florence and Typhoon Trami, sending real-time atmospheric dynamic data to ground-based scientists. Norton also described the Luna HMAP, Tropics, Raven, FirstCube, Asteria, Relic, and L5 SWS CubeSat missions. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:53 p.m., President Milstein adjourned the 2,398th meeting of the Society to the social hour. Temperature, 15 degrees C. Weather, partly cloudy. Attendance in the Powell Auditorium, 83. And those viewing through the live streaming on the PSW Science YouTube channel, 27. Respectfully submitted, James Heelan.
Thank you, James. Are there any corrections or comments on the minutes? Apparently not. So I will entertain a motion from a member to accept the minutes as read. So I have a motion here in the front. Do I have a second? All in favor? All opposed? The minutes are accepted as read and will be posted to the website this weekend, I'm told. Oh, it's my pleasure to introduce tonight's speaker, Steve Squyres. Steve is James A. Weeks Professor of Physical Sciences at Cornell University. There's a lot of other things too. He is principal investigator for the Mars Exploration Rover, co-investigator on Mars Express, and on the Mars Reconnaissance Orbiter, a member of the Gamma Ray Spectrometer team for Mars Odyssey, and a member of the Cassini Imaging team. And previously, he served as a member of the Voyager Science team, was an investigator on Venus Magellan, served on the Mars Observer Gamma Ray Spectrometer team, and was co-investigator on the Russia Mars 96 mission. And before joining Cornell, he was a research scientist at NASA Ames. Steve's research focuses on the robotic exploration of planetary surfaces, especially water on Mars, geophysics of icy satellites, Venus tectonics, and planetary gamma ray and X-ray spectroscopy. He is perhaps best known for his studies of water on Mars and the possibility of a liquid water ocean on Europa that might harbor life. Among other awards, he is the recipient of the Carl Sagan Memorial Award, the Carl Sagan Medal for Excellence in Communication, the Mines Medal, the AAU's Jury Prize, and the Franklin Institute's Franklin Medal. He's an author on numerous technical papers and the book Roving Mars. Steve earned a BA in Geological Sciences and a PhD in Astronomy from Cornell University. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Steve to the podium. Let's see how well we're doing here.
Right here. All right. Thank you, Larry, and it's a great pleasure to be here tonight. So, comets. Comets, when they appear in the nighttime sky, have received special attention from humanity over the years. Now, given the name of our mission, Caesar, I have to start with this one. Caesar's Comet, 44 BC, very shortly after Julius Caesar's death, one of the brightest naked eye comets you could imagine appeared. It was visible in the daytime. It was visible in the daytime, and its appearance shortly after Caesar's death was taken as clear evidence of Caesar's deity. Comets have not always brought good news, however. This is from 1066. This is the famous Bayeux tapestry, and it's depicting the steps leading up to the Norman invasion. This is King Harold here getting the bad news, and look what's in the sky. A comet. That actually was Halley's comet. That was Comet Halley on an apparition at that point, but it came by in 1066 with lots of bad news for King Harold. Now, despite the fact that comets, and there are plenty of other examples like this, have received an enormous amount of attention when they appear in the sky, they remain among the most poorly understood objects in the solar system. And the reason for that is partly illustrated here, perhaps. In 1908 in Siberia, there was an event in a place called Tunguska where something made a very big explosion. Flattened trees for distances of tens of kilometers away from the point of the explosion. No trace of a meteorite was ever found. And while there have been a lot of speculations about what this might have been, the most commonly accepted theory is that the Earth was struck by a comet at Tunguska. And the fact that it created an explosion but did not preserve any meteorite illustrates one of the key points about comets. Comets are so rich in volatile material, material that easily transforms to the vapor phase, that when they come down through the Earth's atmosphere, the heating from atmospheric friction causes them to explode in midair. Boom. You knock down trees, but you don't get anything you can take to the laboratory. So despite the fact that we can see them in the sky, we can visit them in spacecraft, we don't have much in the way of actual pieces of comets, particularly the volatile portions of comets, in our laboratories on Earth. Comets are in weird orbits. This is a plot that shows orbital inclination on the vertical axis, so 180 degrees, that's a retrograde orbit, one going the opposite direction from most stuff in the solar system. This is the semi-major axis of the comet on this axis, and they're all over the place. They're all over the place. The semi-major axes are large. While it's not shown here, the ellipticity, the eccentricity of the orbits tends to be very high. They tend to be in highly elliptical orbits. They come in close to the sun and then they go far away. A lot of them are in very high inclination orbits. There's a bunch of them down here that group together in moderately large orbits, orbits that go out, to the orbit of Jupiter, maybe to the orbit of Saturn. Moderately low inclinations. Those orbits, those comets, those are the only ones you have a prayer of rendezvousing with a spacecraft. because they're sort of in the plane of the ecliptic. They're not wildly eccentric. They don't go way, way, way out far from the sun. And these are called Jupiter family comets. The reason they're in that cluster of orbits right there, they were put there by gravitational interactions with Jupiter. They flew close enough to Jupiter to have their orbit modified, so they wind up with an orbit that has an aphelion, farthest distance from the sun, out near the orbit of Jupiter. Now, when you see a comet in the sky, what you see is this spectacular display of gas and dust streaming off of it. And what people have come to realize is that comets are effectively, the term used for them is a dirty snowball, right? It's got ice, it's got dirt, okay, solid debris. And then when the sun shines on it, especially when it gets in close to the sun, there we go, okay. That's when the sun's heat causes sublimation, transformation to the vapor phase, stuff goes streaming away, and you see that spectacular display along the sky. When it goes far from the sun, is when the comets are relatively quiescent. So what you see when you look at a comet in the sky, you see the head, okay, the coma of gas immediately around it, and the long tail, beautiful tail, streaming away from the sun. This is dust and gas that's being driven away from the comet by solar radiation and radiation pressure. But the heart of the comet is this. The heart of the comet is the nucleus. Okay, and the nucleus is typically a small object. This particular comet nucleus is only about 4 kilometers across. It's made of a combination of rocky material, organic material, and lots of different kinds of ice. And then when it heats up, you can see when the sun strikes this thing, once it starts to getting close to the sun, you get sublimation, gases stream away from it. They carry some of the solid debris, the dust, the dirt with it. But at the heart of the comet is this thing. And that's what we're after. We're after the nucleus. Now, why is it that comets are so scientifically compelling? You can think of comets as being the leftovers from solar system formation. You can think of them as being the early objects, sometimes referred to as planetesimals, things that became planets, the ones that didn't make it into the planets. Most of that stuff gets swept up and winds up being trapped in the planets, but some stuff, just through luck, doesn't wind up being part of the planets. So debris from the earliest stages of solar system formation is preserved in comets. Moreover, unlike asteroids, comets have an enormous amount of this highly volatile material, the stuff that's easily vaporized. That's the stuff that is so hard to get your hands on. But it's the stuff that is, in some cases, the most interesting scientifically. Okay, it is believed that comets were a major source of the Earth's early organic molecules. That's how our organic chemistry first came to Earth, was in part in comets. It's believed that comets were a major source of the water in the Earth's oceans, the water in your bodies. You're made of comet stuff. We all are. And so if you ever hope to understand problems like the emergence of life, how does living material arise from non-living material, having an understanding of the starting ingredients is critical to that. And that's what, to me, makes comets so interesting. Now, NASA has a number of ways that they choose their planetary missions, the missions that they will fly. One of the most compelling is called the New Frontiers program. There have to date been 3 New Frontiers missions selected, built, and launched. One of them was called New Horizons, spectacularly successful mission, flew by the planet Pluto, returned those images of Pluto that you've all seen, magnificent success. That was done by the Applied Physics Laboratory. Mission called Juno, that's a mission that's at Jupiter right now, again, producing spectacular data. One that you haven't heard a lot about yet, but you're going to real soon, is one called OSIRIS-REx. And OSIRIS-REx is a mission to return a sample from an asteroid. That mission is in flight right now. It just arrived at its asteroid. The first pictures of it have just come down in just like in the last week or two. So these were the first 3 missions selected via the New Frontiers program. NASA is soon going to select their 4th New Frontiers mission. 12 proposals by 12 different teams were submitted to compete to be that one next New Frontiers mission. Proposals were submitted in April of 2017. NASA then down selected to 2 finalists back in December of last year. One finalist was a mission called Dragonfly, terrific mission being done by the Applied Physics Lab. I think you might have heard from them a few weeks ago if you were here. And then the other is Caesar. And one of those 2 missions is going to be selected sometime next summer for flight. Now, the science that we will do with the Caesar sample basically breaks down into 3 things. First of all, we can actually see into the past before the birth of the solar system. We expect that comets will contain what are called presolar grains. These are grains that formed in the interstellar medium before the solar system was even born and managed to survive the process of being incorporated into comets. Comets contain a lot of ice. They've been cold their whole lives. There was nothing that was going to melt presolar grains if they're there. So we expect to find those and be able to look at processes that take place in the interstellar medium. The birth of the solar system is believed to be the consequence of the gravitational collapse of a cloud of gas and dust. Okay, conservation of angular momentum says as it contracts under its own self-gravity, it'll start to spin up, and it eventually becomes planets. I make it sound simple, it is not. There are a whole lot of processes, a lot of physics, a lot of chemistry, an enormous amount of complexity in that process. How do you unravel that complexity? Okay, this is a forensic science. It's like a detective looking for clues at the scene of the crime. The only clues left are in comets. And then this is the one that turns me on the most. I already mentioned this. It's believed that comets were a major source of organics, a major source of ices, Earth's oceans, gases that are still present on Earth. And understanding those starting ingredients is a critical part of studying comets. Now you might say, well, didn't we just send, the European Space Agency sent a mission, Rosetta. It was a great mission. It went to a comet, took pictures of it, flew spectrometers, okay, landed a little thing on the surface. It was a great success. Okay, why do we need to go back to a comet again? Because we're going to bring a piece back this time. Sample science. Now, I have spent most of my career doing Mars rovers. And I have spent most of my career building and operating wonderful little instruments that can do science in situ, that can go to, in my case, the curved surface of Mars and make measurements of what's there. But I'm here to tell you, those instruments pale in comparison to what you can do in the laboratory. Laboratory instruments are orders of magnitude more capable than anything that you can miniaturize and ruggedize and put on top of a rocket and shoot into space and actually hope that it's going to work. The other thing about sample science is that samples, once they are returned to Earth, are a gift that keeps on giving because technology marches onward. The very best science ever done with the Apollo samples that were collected back in the 60s and 70s is being done today by scientists who were not born when the samples were collected using instruments that nobody could have imagined back then. So samples continue to produce science for decades and decades and decades to come. Now, I don't expect you to read this chart, but it makes one very important point. On the left-hand side of this is from our first proposal. On the left-hand side is a list of specific testable hypotheses that can be formulated about the nature of comets and what information they preserve about the birth of the solar system, about material that existed before the solar system, about what has been delivered to Earth. You can articulate the hypotheses clearly, and you can then name specific chemical measurements, isotopic measurements, other measurements that you can make to test the predictions of those hypotheses. And those observables are shown on the right-hand side. Again, I don't expect you to read it, but look at the color code. Look at the color code. The stuff in green is the stuff that only requires the non-volatile portions of the comet, the kind of stuff that typically evaporates, that doesn't evaporate away. Okay, the stuff in blue also requires some of the volatile material. So we placed enormous emphasis when we put Squyres together in trying to return both the non-volatile portion of the comet, but also the ice, the gas, the volatile stuff, because there's so much science in that. This is a plot that I love. This shows on the vertical axis over here, this is the quality with which you can measure different stable isotopes. On the other side are molecular detection limits. Okay, notice the break in scale here from 10 to the minus 2 to 10 to the minus 5th, 3 orders of magnitude there. And this simply shows the difference between what you can do in situ with those exquisite, wonderful, ruggedized little instruments that you can fly on a spacecraft. And it compares the sensitivity, lower is better on this plot, with what you can do in the laboratory. Now, these points are all labeled Squyres, but Squyres doesn't make any of those measurements. Squyres enables the making of those measurements by bringing back the stuff. But orders and orders and orders of magnitude of better science. So what's the comet we're going to? It's this one. Churyumov-Gerasimenko. It's got a real jawbreaker of a name. I've gotten good at saying that. This was the comet nucleus that was visited by the European Space Agency's Rosetta spacecraft. Why go back to a comet that we've been to before? Because we know what it looks like. I can tell engineers, okay, I want you to design a piece of hardware that will work on that thing right there. We've seen lots and lots of other comet nuclei. They all look different from one another. Every comet nucleus has its own unique dynamical history. Every one has gone through different spins and orbits, and over time is transformed in different ways. This is the only one we knew well. So we're going to go to one that we know something about. Now, parts of it are terrifying. Okay, that looks like the Matterhorn. Okay, I'm not going to fly a spacecraft anywhere near that. Okay, there are portions of Churyumov-Gerasimenko that are so rugged that you're not going to risk flying $1 billion spacecraft that close to something that nasty. But fortunately, there are other places on Churyumov-Gerasimenko that are nice and smooth. This is hundreds of meters across, very smooth, and this is the kind of thing you can imagine being able to take a spacecraft to. So what's it like down there? Well, turns out, thanks to the European Space Agency, we know. ESA flew a little lander. Its name was Philae, and its job was to actually land on the surface of the nucleus. Now, it didn't land properly. It actually bounced. But as it went through its first landing attempt at this location, it did two things for us. One is it took beautiful pictures all the way down. This picture was taken only 9 meters above the surface of the nucleus. That picture is less than 10 meters across. Okay, so we have very, very high resolution images showing us the exact size frequency distribution of the particles on the surface. The other thing is that when the Philae lander bounced, accelerometers in all 3 of the foot pads were running and told us exactly what the bearing strength of the material was as it came down and then bounced off. If you go an engineer and you say, I want you to build a device that can grab stuff off the surface of the comet, they're going to ask you 2 questions. What's the size frequency distribution of the particles? And how strong is the surface? We know because of this. So we were able to design for this specific environment. Okay, here's our spacecraft. It's a beast. It's very, very big. Enormous solar arrays. The solar arrays from wingtip to wingtip are 43.5 meters, almost the size of almost half the size of a football field. Great big high gain antenna. The reason we have big solar arrays is because we're flying very far from the sun. We have to go out beyond the orbit of Jupiter to rendezvous with Churyumov-Gerasimenko. The reason we have a big high gain antenna is we also go very far from the Earth. And so we have to transmit data back from that distance. When we collect the sample, the spacecraft has a long arm, extends the arm. We take the solar arrays and feather them back so that we minimize the chances of them contacting the surface. This is the last thing the comet sees before we grab a piece of it. This is the spacecraft in the sampling configuration. This is the mission timeline. We launch out here, 2024, get to the comet around 2030, operations until 2032, and the samples arrive back on Earth at 9:40 in the morning, local mountain time, on the 20th of November, 2038. Mark your calendars. I'm eating healthy foods, getting plenty of exercise. My dad's 92. But this is the first proposal I've ever written where I had to have a succession plan. So there's a very capable young hotshot scientist at Cornell named Alex Hayes. And after we launch, Alex is very heavily involved in Caesar right now. After we launch, I'm going to hand the keys to him and sit back and enjoy the show. I'm going to be like that Pope that retired and he just went to a mountaintop villa outside of Rome. That's going to be me. Our mission is enabled by a form of propulsion called solar electric propulsion. Basically what it does is it relies on electrical power generated by those big solar arrays to accelerate atoms of, in our case, xenon to very high velocities. This is what the thruster looks like when it's firing. And what it does is it produces a very gentle thrust. It's not a very strong push, but it fires for years. It's a rocket motor that you can fire for years at a time. And what it does is enable you to fly these complex kind of spiral trajectories, which is what we need to match orbits with the comet and then match orbits back again at Earth. This plot shows the trajectory itself. Outbound, we have a lot of time at the comet. We have 4.5 years at the comet, most of it very far from the sun, and we do that intentionally. We do that intentionally because comets, when they're close to the sun, that's when they're shedding debris. That's when there's dust, that's when there's gas streaming off of them. You don't want to be close to a comet when it's doing that. So what we do is we wait until the comet is out at like the orbit of Jupiter, where it's icy cold. The activity dies down, it's safe to approach, and our solar arrays are so big that even beyond the orbit of Jupiter, we can do full-up operations, including sampling. I won't spend a lot of time on this slide. It's a complicated one. It shows the entire mission sequence. The story that it tells is, the essence of it is what you do when you get to the comet is you feel your way in very carefully. Okay, you get close enough to get a look at it. You get a first sense of what the gravitational field is like. You figure out the effect it's going to have on your spacecraft trajectory. Once you got that figured out, then you go down a little closer, map it some more, a little closer, map it some more. Now we have a huge advantage over every other mission that's tried to do anything remotely like that, in that we have already got good data for what Churyumov-Gerasimenko looks like. But comets change. As they shed that debris, as they shed that ice, and as they shed that dust, their shape changes, their spin rate changes. So we're planning everything that we need to do to map it all over again. But we got years to do it, so we got lots and lots of time in our timeline. And in the end, we'll have a very, very good understanding of the gravity field and the shape and the topography of the comet before we go down to the surface. All of that's enabled by a suite of cameras. The cameras are the only scientific instruments, really, aboard the spacecraft. Aside from a few instruments that monitor the state of the sample once we've collected it, these are the only science instruments we fly. Why? Because we don't need them. All we got to do is grab a sample off the surface of a nucleus that's already well known. The science instruments on Squyres are all in the laboratories in 2038, waiting for that precious sample when it comes back. That's where our science instruments are. So what we got is a suite of cameras. They're all based very closely on cameras that have flown before, very mature, very low risk. One of the themes that you'll see running through Squyres over and over and over and over again is risk reduction, risk reduction, risk reduction. We're trying to do something that nobody's ever tried before. It's very difficult, it's very risky, so what you do is you buy down risk everywhere that you possibly can. How do you select your sampling site? The way we do it is with 4 maps. And we've actually done preliminary versions of those 4 maps. We call them safety, sampleability, deliverability, and science value. Safety, they're all color-coded, green or red. Green is okay, red is not okay. Safety is just what it sounds like. What are the places that are safe to go with the spacecraft? So for example, one of the things that goes into the safety map is it's only safe if you actually have a clear line of sight to Earth when you're going down to the surface and doing the sampling. If you don't have a clear line of sight to Earth, we don't know what the spacecraft's doing. That's not safe. That's one of the things that goes into the safety map. Sampleability, that is pieces of the nucleus that, remember I told you some places look like the Matterhorn and other places look like a rocky beach. These are the places on the nucleus that have properties that are compatible with demonstrated capabilities of our sampling system. So lots of red, lots of green. Deliverability is the ability of our navigation system to actually deliver the sample to the surface, or the spacecraft to the surface. Science value, 50 shades of green, okay? Comets are so interesting that the science is going to be good everywhere. But there are some places that, for various reasons, we think have more ice, for example, and so those are ranked higher. You take those 4 maps, you merge them, and the places that are green on all 4 maps are the ones from which you choose. And we've chosen some potential sites for sampling. Of course, we're going to do this all over again out in 2030. And here's one of them. The yellow circle shows the exact 3 sigma accuracy with which we can target the spot on the surface. And that's one that we know we can get to, know has good properties, and that we feel very good about from a science perspective. Now, the form of sampling that we use is what's called touch-and-go sampling. This was done by the Japanese Hayabusa mission at an asteroid. This is being done by the OSIRIS-REx mission at an asteroid, and basically it entails flying your spacecraft all the way down to the surface, touching it for a very brief moment of time. In our case, it's 5 seconds, and then getting the heck out of there. Okay? Now, this explains the whole thing in detail, but a better way to get a sense of what TAG looks like is to just watch it. So let me play you a video. Okay? So what you're seeing here, green is the spacecraft trajectory. There's Churyumov-Gerasimenko. Here's the spacecraft. This is not a cartoon representation. This is the output of a full dynamical simulation of the touch-and-go process, including navigation errors, maneuver errors, and firing thrusters. Everything is in this. So first maneuver there was at a place called TIP, trajectory interface point. That's when we start to head down on towards the surface. There's the spacecraft with the solar arrays now feathered back. We are now flying to a place called checkpoint. You can see the altitude above the surface. There's the altitude there. We are now, let's see. Yeah, so we're 160 meters above the surface. There's the shadow of the spacecraft. What you're seeing on the left is what would actually be the view through the navigation cameras. There's another maneuver at a place called match point. That's the last burn that we do. What we're doing is we're computing firing solutions for those burns from the pictures that we see and the data from our laser rangefinder. And now we're just simply falling towards the surface. And the arm is a pogo stick. In the forearm link is a compressible constant force spring. So when it touches the surface, the spring compresses, holds holds the sampler in place for 5 seconds or more, and then the spring, there we go, compresses, expands back out, and off we go. It's quick. This is a purse snatching. This is our arm. This is the sampling arm. This is it folded up in the stowed configuration. Here it is in the extended configuration. Very simple, 3 joints, 3 long lengths. The whole thing fully extended is about 4.5 meters. At the end of it is the business end of this thing is the sample acquisition system. This is it in a rendering. Here's the actual hardware. It's a beautiful, beautiful piece of hardware. It looks like something that Darth Vader would have in his living room, but it's really cool. Now at the heart of it, and you can see it on the inside, that kind of golden glow there. At the heart of it is the sample container. This is the thing that will receive the sample. Okay, it's coated with gold everywhere. Why gold? Because it's non-reactive. Okay, we don't want chemical reactions to take place with the walls of our sample container, so we make it out of gold. There is a sapphire window at the top, which I'll explain in just a moment. Total volume of this thing is about 1.5 liters. It lives inside the sample acquisition system, and this shows how it works. The first thing to contact the surface are these spikes. We call them ripper tines. We didn't make that up. That comes from agricultural machinery. But these are spring-loaded spikes. They're curved and spring-loaded in such a fashion that when they penetrate the surface, they splay outwards, breaking up the material. Now, we think these are probably unnecessary. Based on what the Philae lander or the Rosetta lander saw at the landing site, we probably don't need these at all. But just in case we get to a place where the surface particles are really stuck together, we include this. Then the real work, once the ripper tines have penetrated the surface and disaggregated if it needs to be, the real work is done by these 12 compressed nitrogen jets. We have gas bottles, compressed gas bottles. You can see them out there on the arm, right there. And what they do is they force compressed gas through those nozzles, and what it does is it drives sample material through 4 doors. There's one of them, covered by Kapton covers. 4 doors in the sample container, so it blows sample material into this. So that's how it's supposed to work. To test this, however, you have to test it under the appropriate environmental conditions. The appropriate environmental conditions for this device are 0G and vacuum. Simultaneous 0G and vacuum. So to convince yourself and convince NASA that this is going to work, you got to test it under those 0G vacuum conditions. There are only 2 places you can go to get that. One of them is space, and the other one is Cleveland. We chose Cleveland. At NASA's Glenn Research Center, there is an extraordinary facility. It was built back in the 60s. There is this vertical shaft, 580 some odd feet deep, dug by hand with guys with picks and shovels in the 60s into the shales along the shore of Lake Erie. 580 feet deep. Lined with steel, capped at both ends. It's an enormous vertical vacuum chamber. You can pump the air out of it. Then, what they do is they will load your experimental apparatus into a drop vehicle. Here it is here, so our Comet simulant and all our hardware is inside of that. Seal it up, pump out all the air, drop it. You get perfectly clean 0G and vacuum for 5.18 seconds. We need 5. It's like it was designed for us. And the whole thing lands, I swear to God, in a giant vat of styrofoam peanuts. Science is really fun. We have spent weeks and weeks and weeks at this facility. In fact, I had part of my team out there just this past week. Here's one of our test teams. At the facility on the right, you can see the sample acquisition system in the chamber. This video shows you, oh, wait a minute, I forgot to tell you something important. I left something out. There's a camera. There's a camera right there. Remember I told you there was a sapphire window? So there's a camera built into the SAS that can see right down into it and can take video of the sample as it actually gets acquired. So here's what the view from that camera will look like. This is in one of our tests at Glenn. Here we go. Oh, wait, hang on. Oh, I lost the cursor. There we go. This is 0G and vacuum. Oh, come on. There we go. Just fills up with sample. It works really, really well. And we need about 20 grams of sample to do all of our science. We are required by NASA and intend to set aside 3 times that for future investigators. So we need a total of 80 grams. In the test with this thing, we routinely get 200, 250, 300, 300 plus grams of samples. So it works really well. Now, once you get the sample, you need to determine how much you got. We can determine what volume of sample that we got from the pictures. We can actually physically see it. But we also care about the mass. We need to weigh it in zero gravity. The way you weigh it in zero gravity is you produce artificial gravity. We have a long arm, and we can swing it in an arc, produce a centripetal acceleration, and then we measure with a simple force torque sensor how much force is generated by that, and we can convert that into the mass of the sample. Fine and dandy in practice, in principle. In practice, you have to test it. Now, in order to test this, you'd like to do it in 0G, but you actually don't have to. You can do it in 1G as long as you have an incredibly big and incredibly smooth and incredibly flat table. It's like air hockey, you know, where you have a little tiny cushion of compressed air, and as long as that big table is perfectly smooth and perfectly flat, you can do what's called a gravity. It's called a gravity offload table, and what you can do is you can swing the arm. Okay, and it's riding on that cushion of air, and that table is so flat and so smooth that it introduces no little perturbations, and you can get a valid measurement and demonstrate that the technique works. To do that, you need a really, really, really big piece of granite. Granite gravity offload tables are the gold standard in this business. We purchased for our project what is now the largest slab of granite gravity offload table in the United States. There's one almost exactly this size, I believe, at the Naval Research Laboratory, very nearby. So when we bought ours, we made it an inch longer, an inch wider, just so we could say that. It's installed in the robotics facility at the University of West Virginia, where they've been testing and testing and testing. This is from some of our early tests. Now, that may not look much to you, but it cost me $40,000 just to ship that rock across the country, okay? That was a very expensive test, but what we find is that, yes, indeed, we can measure the mass this way. Once we have convinced ourselves that we've got enough sample, then it's time to stow it. The first thing that we do is we jettison the sampling cone, and what that does is expose that beautiful gold sampling container. We then reach the arm around. It's got 2 elbows, so we can reach it around and insert it into this. This we call the sample containment system. And what we're going to do with this is we're going to hermetically seal the sample. Now, robotic hermetic sealing under dirty, dusty conditions is a very difficult thing to do. And this is a technology that we put an enormous amount of money and effort into. The way it works, insert the sample container, it latches at the bottom, tug to make sure that it's in there, then you release it. There it is. We have a lid that we swing over, and then there's a set of fingers that come up and grab the lid and pull it down hard. Enormous amount of force. Those fingers pull down with very, very high force, and that high force is the key to making this work. And what it does is it drives a very hard stainless steel circular knife blade into a softer metal copper gasket. So it's a knife edge seal, drives that knife blade into the copper, and we've tested this at very low temperatures. We've tested this with the seals very, very dirty, and as long as you got enough preload, enough force, you can overcome that, and we can get very, very low leak rates. So we can seal the sample up. So what you see at the lower right there, that's what the thing will look like, minus the cool logo. But that's what it will look like when the sample is sealed. So now your sample is sealed up. It can't get away. The ices are all in there, and you can just bring it home, right? Except you can't. The problem with that is that what that creates is a situation different from anything that would occur naturally on a comet. Because you cannot keep, we have no way of keeping that thing at cryogenic temperatures. Temperatures hundreds of degrees below zero, all the way back to Earth, including the descent at 12 kilometers per second through the Earth's atmosphere with your sample return capsule being heated up to 3,000 degrees on the outside. We can't do that. Not for $1 billion. Give me $2.5 billion, we'll talk, okay? But a $1 billion mission, we can't do that. So then what happens is that sample is going to warm up. And what that means is some of the ices are going to undergo sublimation. CO2, water vapor, they're going to come off. And what happens when that happens on a comet, the stuff can get away. It flies away. That's what it makes it look like a comet. But inside that sample containment system, it's trapped. It can't get away. And it's held at high pressure immediately adjacent to the solid sample. And chemistry can happen, and it will. Chemical reactions will take place that will alter the sample. All this evidence that you went there to get, you start to destroy it because of chemical reactions that you have allowed to take place. So you gotta separate that icy stuff from the solid sample and do it in a way that preserves the solid sample. Our device for doing that is shown here. We call it the gas containment system. On the left, you can see a rendering. On the right, actual test hardware and a very expensive thermal vacuum chamber at NASA Goddard. Here's how it works. Let me take this apart for you. So we have the sample containment system on the inside. Oops. All sealed up. It's got the sample in it. Tank around the outside is going to receive the gases. This is simply an empty tank, lined with high purity gold, again, so you won't get chemical reactions. And then there's some plumbing that connects the two. There it is again. So you have the tank, that's the C-shaped thing along the top. You have the sample container, and then a lot of valves and plumbing and sensors. So there it is. I'm going to give you a simplified view. Okay, so here's how it works. Look in the lower right. We put the solid sample into the sample containment system. We cinch down the lid, and we hermetically seal it. Now, what we do is we gently warm, and I'm talking temperatures of like maybe 30 degrees below zero, not real warm. But we gently warm the sample to the kinds of temperatures that it might experience when the comet goes close to the sun and it starts boiling off all that stuff. But then we have plumbing that allows that gas to go into the tank. And the tank is kept icy cold, many tens of degrees colder than the sample. The tank is kept cold by a radiator. So what we're doing is we're passively cryopumping those volatiles into the tank. We allow that to go on until, and we're sensing temperature, we're sensing pressure, we're sensing the partial pressure of water vapor, we're sensing the partial pressure of carbon dioxide all through this process. Once we are convinced that we've got all the gas that we want to get, then we toggle two valves. And boy, you better do this in the right order. The first valve you close to seal off the tank. And so now that precious volatile sample, which has been separated from the solid sample, is sealed up in there, can't get away. And then you open a vent valve. And any remaining gas is just vented to space. It's gone. That's fine. We don't care because we got most of it. We get about 5/6 of it. Okay? And that's the configuration that you fly in all the way back to Earth with your precious sample stored in contact with vacuum so nothing bad can happen to it, because that's the non-volatile stuff. And then just before Earth entry, you close that valve. And what that does is prevents contamination of the sample by the Earth's air once it's come back down through the atmosphere. Here's what the whole thing looks like. It's actually a really simple device. It's pumps, it's valves, it's a tank. I got some of my GCS team here tonight, and they must hear me say it's simple and just be ready to throttle, babe. But there are nuances, okay? There really are. But it works very, very nicely. Now, one other thing that's nice about this, if you look, if I can show it, okay, shown in black here, these are housings that contain a phase change material. The material is a hydrocarbon called dodecane. And it's a material that has a melting temperature of about -10 Celsius. We do not want the ice that's going to form in this tank to ever melt. Because if it melts, there are isotopic equilibration reactions that could take place that'd be really bad. So we want to keep this thing frozen all the way down through the Earth's atmosphere and on the ground at the recovery site long enough that we can recover it and get it into cold storage. What that phase change material does is it buys us time. This thing lands on the ground. It's still pretty cold. It's below -10 C. We don't want to get to 0 C. It warms up, it warms up, it warms up, but as soon as it hits -10, you start that phase change and the temperature plateaus. And it plateaus and it plateaus and it plateaus, and you don't have any increase in the temperature of the sample until all of that dodecane has melted. And then it will start up again, and that buys us hours. This is our sample return capsule. We get back to Earth. We need to seal it up in a little spacecraft that can survive the fiery descent through the Earth's atmosphere and get that sample safely onto the surface. Our sample return capsule is being provided to us by JAXA, the Japanese Space Agency. It is based closely on the design of the sample return capsule that flew successfully on their Hayabusa asteroid sample return mission. We close up the gas containment system. We take the aft portion of the sample return capsule. We drive it upwards into that big golden dome. That's the heat shield. Seal it up, and then we release it. The way we release it is we put the entire massive spacecraft on a collision course with Utah. We fly the entire spacecraft towards the state of Utah. We release the sample return capsule, do a divert maneuver with the main spacecraft, target the sample return capsule very carefully. We don't want to hit Salt Lake City. We got a special place that we want to hit. And it enters the Earth atmosphere going 12 kilometers per second. Now, as I said, this is based on a Japanese sample return capsule design. And one of the things that I love about this sample return capsule design is right there. While it's still hanging on the drogue parachute, we drop the front heat shield. This is a characteristic of the Japanese design. So what you've got is you've got the outer surface of this heat shield that is heated to 3,000 degrees. And that heat starts to leak through the heat shield towards the sample. And just as the sample temperature is starting to go up by about a degree or two, boom, you drop the heat shield. And so there's nothing left but the cold breeze of a November day in Utah flowing by your sample on the way down. And you can see the configuration that it looks like that it's in as it's coming towards the surface. This is not conjecture. Again, we've built hardware. These are parachute tests, drogue chute and main chute, done in Japan. Where we're going to land, one of the strangest places you've ever been in your life. This is called the Utah Test and Training Range. It's a place where the United States military goes to blow stuff up. It's a giant dry lake bed to the southwest of Salt Lake City. It's just this enormous 100-kilometer flat expanse of mud. So it's soft. And it's saline mud. It's salty mud, so it doesn't freeze in the wintertime. You get your boots nice and muddy when you go there in January. We've done that. And so what we do, you can see this is the Utah Test and Training Range. It's restricted airspace. It's restricted ground space. Where we land fits neatly within the restricted area. This green ellipse that you see there, that's our 3 sigma landing ellipse. We'll land somewhere in there. We have 2 helicopters that will be staged right outside the landing ellipse. We have a Hill Air Force Base range radar is able to track this thing to within meters all the way down, so we'll know exactly where it lands. Okay, after it touches down, they will send radar vectors to the helicopter pilots. They will fly to the sample return capsule. They will pick it up, and then we have a mobile cold storage unit. We call it the ice cream truck. And this thing will pick it up, latch it, fly it back, and get it into the ice cream truck in a time that is short enough with substantial margin to allow it to stay frozen the whole time. Sounds easy, right? Again, you better prove you can do it. So we did. And we went out to Utah and we did a bunch of tests. This is our test team that was out there, 2 helicopters, tested all sorts of nominal, off-nominal scenarios, everything go wrong you can imagine. For worst case weather conditions, we have something like 4 to 5 hours on the ground before we have to worry about the sample melting. In our worst case test, we got it into the ice cream truck in 40 minutes. So I feel very good about this. Then there's curation. Once you've got that sample back, this precious $1 billion worth of Comet, it's cold, it's frozen, it's safe, but it's still in Utah, okay? And you got to get it someplace where you can actually start to take it apart and do science with it. We do our curation at NASA's Johnson Space Center. This is where planetary materials have been curated since the beginning of the planetary program, from Apollo onward. It's not a simple process. There is some disassembly required. But we have built our hardware from the outset with curation in mind. We have procedures that we've worked out and tried out for extracting the solid sample. We've worked out how we're going to get the gas sample out, and we believe we have a curation process that will keep the sample safe and ready for science for decades to come. And then the science begins. Thank you very much. And I would be happy to answer any questions you might have. I'll just warn you, I can talk about this all night, so.
Some people with microphones. Where are they?
There's one.
There's one. Red microphone. Do we have another microphone runner? Anyway, if you have a question, put your hand in the air, and when the microphone comes to you, it will be on. Hold it close to your mouth and ask a question. Hold your speeches for afterwards. Okay, red microphone there. That would be Frank. Thank you.
Again, Frank Robert, a member. Fabulous talk. Thank you very much. Just an odd side question. If you're using nitrogen jets to blow the debris into your chamber, how do you avoid skewing the results with nitrogen reacting in there with what you're actually getting?
Well, actually, I mean, first of all, it's only going to be in contact with the sample for a very, very brief period of time. It's a matter of seconds. But nitrogen is actually, for almost every geochemical, chemical application, an inert gas. In fact, the curation environment at Johnson Space Center for all of their astromaterials, the lunar samples, samples from the Stardust Comet sample return mission, it's all stored, it's all curated under very pure dry nitrogen, just as we will be using. So we don't anticipate any chemistry taking place as a consequence of that.
Thanks.
We have another question, and raise your hand, and the mic will come to you eventually.
Brian Hart.
Okay.
I'm not a member. I just was wanting to know, can you talk about any of the risks to the probe itself as it transits through the solar system on the way to the destination, in particular through the asteroid belt? Any risk to damage to especially those big solar panels from particles?
Yeah, the risks that you encounter are very much in family with the risks that are experienced on many, many other planetary missions. There's nothing unusual about this. Anything that goes significantly beyond the orbit of Mars, certainly anything that goes to Jupiter further on out, you are going through the asteroid belt. We know from many passages through the asteroid belt that, I mean, it's not like in the movies. It's empty space for the most part. There is a radiation environment, but the radiation environment is minor compared to what you find when you, for example, when you orbit at Jupiter. So like the Juno mission is a good point of comparison. Juno mission has very big solar arrays, not quite as big as ours, but quite large. They had to pass through the asteroid belt. They did that just fine. They are operating in the Jovian magnetosphere, which is a very intense radiation environment. And they had to put in place a lot of complicated measures to make sure that they could deal with that. Our job's actually much simpler as far as that's concerned. The environment that I think is the one we're most concerned about is the dust and debris environment immediately surrounding the comet. We have two very important things working in our favor on that. First of all, again, Rosetta, they've been there. Okay, they've measured it, they've characterized it, we know what that environment is like. Moreover, all of the Rosetta data are when the comet was closer to the sun than when we will be doing everything that we're going to do. We're intentionally doing our operations when the comet is farthest from the sun. So even though we know what the Rosetta environment was like and they survived that just fine, we know that ours will be less stringent. So in terms of the environments that this spacecraft faces, you know, I've been involved in spacecraft that landed on Mars. This is a much easier environment than that.
Blue microphone there, and then
Melanie Rowland, not a member.
Cool.
I was wondering, will the comet have undergone any outgassing since we were there with Rosetta?
Oh, absolutely.
How do you adjust for differences in topography from what the Rosetta mission?
Yeah, you can calculate the amount by which the topography will change, and it's measured in meters, you know, not tens or hundreds of meters. So the changes should be relatively modest. Nevertheless, to be very safe, we have designed our entire orbit and mapping plan as if we don't know what the shape is going to be at all. We have all the margin that we need if it were a completely different comet to map it should we need to. We don't expect that. Okay, we expect the changes to be relatively modest. The changes are actually, in my way of thinking, a good thing because as just simply part of the natural process that we have to go through to map the nucleus and select our sample sites, we will also beautifully characterize a nucleus that had been very well characterized by Rosetta 2 perihelion passages earlier. So we'll be able to actually visit a comet after it's been close to the sun twice and see what happened. And there's the morphologic changes that will take place, will I think be very interesting scientifically. But we expect the changes to be modest. We are totally prepared for them not to be.
red microphone.
Timothy Thomas, I'm a member of the Society. You've got a lot of salaries here. You've got a lot of very expensive equipment. You've done some very expensive tests and purchasing. You mentioned one table for $40K to move it.
Yes.
Yet you're not selected to go. So a lot of this is just luck.
We did get, as the Dragonfly team did, both teams got $4 million from NASA after our step 1 selection to do some of the work that we do. And all the other work that we've done on our own nickel. We try again.
Well, I think you mentioned it doesn't all go to waste. The granite slab is going to be used.
Oh yes, yeah. I mean, a lot of the test facilities will be valuable for other purposes.
The most inert thing will be.
But the point here is an important one, and that is that once you have this whole process is one of convincing NASA that you've got an idea that's good enough that the taxpayers should be willing to spend $1 billion on it. You better have a pretty good story. Okay, part of it is having a good science story. Okay, and we feel real good about our science story. I think the Dragonfly team can and should feel really good about theirs too. So once you get to the second stage of the competition, it's mostly about demonstrating that your technology, your cost story, your schedule story that those are all robust, that you got all the margins that you need. And what that comes down to in very large measure is significant upfront investment in technology development. And that's exactly what we've been doing. Risk reduction, risk reduction, risk reduction.
Green microphone, then red microphone.
Mark Saul, member. The Tunguska Comet, how
Yeah.
come nobody saw it coming?
How come nobody saw it coming? It probably wasn't very big. It probably wasn't a very big object. It could have been tens of meters in size. And this was 1908. Observing was not what it was, not what it is today. So it's not a surprise that we got smacked.
Red microphone.
I'm David Rosen, lifetime member. Will you, in your preliminary investigation of the comet, will you be able to figure out the exact mass and density distribution of the comet?
Yeah, we can do that. We will get a very good shape model using our cameras. We also have a laser altimeter, laser rangefinder, which will help to define the shape very precisely. So we will have the shape, we'll have the volume. The bulk density will be easily measured by determining the gravitational attraction of the comet on our spacecraft. So simply spacecraft tracking will yield a mass number pretty quickly, and with time will yield details about the shape of the gravity field, which tells us something about the mass distribution. Now that all, of course, has been done very well for us once already for Churyumov-Gerasimenko as it existed at the time by Rosetta. So we have that shape model, that mass distribution model as a starting point, and we'll be looking for deltas off of that. But yeah, we can determine all of that. And it was done pretty well by Rosetta.
Blue microphone, then green microphone.
Kirby Runyon, and I am a member. Very interesting talk, Steve. Thank you. And my question has to do with redundancy when you're at the Comet.
Right.
If your first sampling attempt is unsuccessful at gathering material, how many chances do you have, and how can you troubleshoot some of those known unknowns?
We have enough consumables for at least 3 full attempts. And when I say a full attempt, I mean an attempt that is preceded by 2 rehearsals. So we do a rehearsal and we back away. We do another rehearsal closer down and we back away. If both of those go well, then we attempt a sampling. Okay, we are able to do that full sequence, should we choose to do it, up to at least 3 times with the amount of consumables, the propellant, and the nitrogen gas that we have on board. Probably we could squeeze out a few more than that. So we have the capability to go at it over and over again. The key thing is that we also have an enormous amount of information about what happened during the actual touch and go sampling event itself. I didn't spend a lot of time talking about the cameras, but we have a couple of cameras that are exclusively devoted to recording the dynamics of the interaction of the sample acquisition with the surface. Of course, we have that one camera that's built into the SAS itself that sees into the sample container so we can see what's going on in there. But we also have another camera called TagCam, which just views the field of view is filled by the sample acquisition system and the surrounding several meters of comet, and it takes video of that interaction. So we'll be able to watch that interaction. And of course, then we have engineering data that will tell us, how strong the surface was. We will have imaged the surface right before we contacted it and right after we contacted it. So there's an enormous amount of forensic information that we would be able to use to piece together if a tag event didn't go well, why it had not gone well. And as I said, we can do at least 3 of those, each of them preceded by two rehearsals. So it's a pretty robust system.
Green microphone.
I'm Noah Katz. I'm not a member. You had said that the nucleus serves like a planetesimal in the formation that would be similar to those that would be presumably formed that would make up planets in the inner solar system as well. How much of the data will be able to be used to extrapolate about the planetesimals that could have formed Earth or Venus or anything, given that there could be different compositions depending on how far away the planetesimals formed from the sun?
Yeah, that's a good question. What we're trying to do with a comet sample is find the material that is closest to the original primitive composition of the solar nebula. So the closer to the sun that something condensed and formed, the more likely it is to differ in bulk from the composition of the solar nebula. If you form really in close to the sun, the volatile stuff just isn't going to condense at all. So the planetesimals that form in close, probably represented well by our meteorite collection, not represented well by comets. The further out you go, farther, you're going to find more and more volatile material. And so if what you want to do is understand the starting composition, you want to go as far in that direction as you can. Now, is a Jupiter family comet the farthest you can go? No, it is not. Okay, and if I could go out into the Kuiper belt and sample an object at cryogenic temperatures and bring that back, it would be even better than this. Like I said, if you want to talk about giving us a few $1 billion, we can have that conversation. At $1 billion, this is pretty darn good.
I think we have the blue and then we have the red. I'm sorry I didn't see you, so you're next.
I'm Bob Hershey, I'm a member. What kinds of things do you expect to get answers to from having the physical samples that you weren't able to get remotely?
I'll give you one really, really good example. Okay, really, really good example is to obtain with very, very high precision stable isotope ratios. A terrifically important one is the stable isotope ratios of oxygen, O16, O17, O18. Okay, oxygen stable isotopes, none of those undergo radioactive decay. They're present in various ratios in different materials. Each one of those ratios, sets of ratios, is a specific fingerprint that tells you something about the reservoir of oxygen from which something came. Okay, so if one of the things that you seek to understand is where did the Earth's oceans come from, okay, we know what this O16, O17, O18 ratios are in the Earth's oceans. We know that very well. We know what it is for certain meteorites. We know what it is for Mars because we have meteorites that come from Mars. What is it for comets? Nobody knows. It was undeterminable by the Rosetta spacecraft. They were not able to constrain it. It's a hard measurement to make unless you actually have the stuff in the laboratory. So that's one good example. Xenon's got, I forget, 7 or 8 different stable isotopes. There's wonderful things you can do with the isotopes of xenon. There's a whole bunch of very, very high precision stuff that you can do. The other thing, one of the things that fascinates me the most is, we have, in our proposals, we have these tables of, sensitivity to different, we get a list of molecules that are known to be present in comets. Okay, and the sensitivity of the Earth-based instruments. And, for these molecules, you got the detection limits are picomoles. I mean, it's incredibly small quantities. So we can demonstrate that for all the molecules in the zoo of known comet volatiles, we can detect it. But what about the ones that we don't know are there? See, that's one of the things that fascinates me is I think that we're going to find a whole bunch of chemical species that have never been detected in comets because they're hard to detect remotely. But if you can get that gas into terrestrial laboratories, to me, some of the most interesting stuff is the stuff that you just can't predict.
Hi, Chris LaFeria, not a member. My question is that 67P is obviously a very interestingly shaped comet, so I'm wondering if you're expecting significant compositional differences between the different parts of the comet, and if so, how would you think about that in the way of?
That's an interesting question. So what she's referring to is that sort of bilobate shape of Churyumov-Gerasimenko, and it's been suggested that that could have actually formed as 2 cometesimals kind of kissed each other and didn't let go, right? So could the 2 lobes have different compositions? Yes, it's entirely possible that they do. We are not going to be sampling the bedrock, if you will, of either one of those lobes, okay? That's that rocky Matterhorn looking stuff that I'm too scared to go close to, all right? What we're going to be sampling is that debris that settles in the smooth terrain. Now here's how that debris forms. When the comet goes close to the sun shines on the Matterhorn stuff, if I call it that, the rugged terrain, and pieces of it are liberated from the nucleus by sublimation. Sublimation causes it to fall apart and chunks come flying off. Now the little chunks are easily swept away by gas drag. The bigger chunks tend to go up and then they get out of the jet and they fall back down on the surface. And what happens is they collect in these gravitational low spots. That's where they gather, and that's what the smooth terrain is. The nice thing about that smooth terrain stuff is it's receiving infall from all over the comet. So we believe by sampling the smooth terrain, we can actually get material that is from all over the original spot on the nucleus. Now, we will not be able to look at a particular grain in our sample and say, oh, that one came from this part of the comet, and oh, that one came from that part of the comet. We will not know that. But if there is diversity on the nucleus, we will see it in the diversity of the particles in the sample.
Is the green microphone out there somewhere? Ah, please.
Hi, Michael Katz, not a member. Very much enjoyed this. Thank you. Curious about the notion that the science goes on for decades. You mentioned the Apollo samples,
yep.
And I'm curious how you maintain the integrity, and if you're making this journey, and would it have been considered? Did you consider taking two separate samples so one could be examined and inspected, with the current technology, and another one kind of put on cold storage?
We do exactly that. We do exactly that. I mentioned it briefly. I'll say it again. We are required by NASA, and we fully intend to set aside at least 75% of the sample that comes back for other investigators in later years. So if we bring back 100 grams, we get 25 grams to work with on our team, and 75 grams is set aside for later generations, later instrumentation, and so forth. Those are carefully curated, so they're preserved under conditions that will not lead to alteration of the sample. So as you can imagine, you're talking about very, very low temperature curation for a Comet sample. And some of that stuff's going to be probably preserved for decades.
But you're confident in the ability to separate the current versus the future sample?
Yeah. We lay out the whole process by which we do that in our proposal. This is what has been done for every planetary sample return mission. There's a preliminary examination of the sample. And what we are expected to do is, out of that, let's say it's 100 grams, we select 25 grams that is representative. Okay, so what we're going to have is a lot of particles, okay? And we can't just cherry pick the 25% that look to be the coolest. We are required, and I'm totally on board with this, to pick a representative sample that's our 25%, and then a representative 75% is left behind. Now, for the ices and the gases, keeping it representative is going to be easy. For the particles, there's some effort that goes into that, and we talk at length about that in our proposal, how we're going to go about that. But yeah, it needs to be representative, because the best science is not going to be done by our team. Okay, we're going to have the best instruments that money can buy in 2038, but in 2048, it's going to be much better.
I think that's the last question.
Oh,
so
okay.
yeah, unless there's more, are there more questions? Okay, that's the last question.
One more.
One more?
One more. Two more. Okay.
Two more. All right, good.
Allison Duck, not a member. What challenges do you expect that would be different than those faced by the Hayabusa team?
Well, the primary challenge that is beyond what was faced by the Hayabusa and Hayabusa 2 team is that they're doing asteroids and we're doing comets. So all the differences between comets and asteroids apply. Very elliptical orbit, much harder to match orbits with. That's why we've got the solar electric propulsion system that we have. Lots of debris coming off the nucleus. You got to sample at cold temperatures. You got to separate out the volatile from the non-volatile stuff. None of that is stuff that you have to worry about for an asteroid. Don't get me wrong. Sampling an asteroid is plenty hard, and I've got enormous respect for Hayabusa, Hayabusa 2, OSIRIS-REx. What they're doing is magnificent and very, very challenging. We're going to take it the next step.
Another question? Right here?
Yep.
Okay, green mic.
Hello?
It's on.
Hi, my name is Jacob. I'm not a member. I was just wondering how other space agencies from other countries are involved in this. Obviously, you have you've borrowed some technology from Japan for the reentry, but if any space agencies are interested in, or you're giving any samples to them after the mission's complete.
The primary contribution from another national space agency is the sample return capsule from JAXA. We have a number of Japanese scientists on our team who are sample scientists who will get significant quantities of the sample to analyze in Japan. We have a number of German scientists on our team. Those are actually mostly people who were involved in the Rosetta mission, particularly in the Rosetta camera experience, because we want to benefit from that experience. Those are the two primary international involvements in CSER. Now, of course, once the sample has come back to Earth and we've gotten our 25%, the remainder of it that is going to be analyzed by the rest of the science community, NASA will have a process for allocating that sample. And I have no say over what happens to that portion of the sample. I'll just express my opinion that it would be foolish to exclude any of the world's best laboratories if they got something to bring to the table. It's not up to me.
Any other questions? There being no other questions, let's thank the speaker.
Thank you very much.
So in appreciation for coming down here from Ithaca and giving this talk, I'd like to present you with this framed copy of the announcement of this lecture, signed by all the members of the General Committee on behalf of the membership, and also a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington.
All right.
Covering the years, 1871, 1874, and includes the original bylaws and the original members and the speech by Joseph Henry explaining why the society was formed and why they named it the Philosophical Society of Washington.
All right.
Okay, thank you.
Thank you very much. Thanks a lot, folks.
Before we go, I mean, adjourn to the social hour, a few closing items. PSW depends on its membership and supporters and sponsors. And if you are not a member, we would invite you to join. So we have the dread how to join slide. It's very easy. You go to our homepage and you'll see the join button up in the upper right-hand corner. About the middle of the screen here, when you press on that, it'll pull up the next screen, which has the membership application button, which you then press to pull up, believe it or not, an application for membership, which you fill out, including all of the required fields marked by the red asterisk. When you get to the bottom, it will say submit form. So when you press that button, it will submit the form and bring up a payment page, which I didn't bring up because I don't want to pay again. But if you fill out the payment page, it will ask you to pay your dues. You can do that with a regular credit card. You do not have to use PayPal. And your application will be transmitted electronically to the powers that be. And in all likelihood, you will be admitted to membership. And if not, we will return your dues payment, which so far has not happened in the last 2 years. So I assume that we will admit you to membership. PSW is a 501c3 charitable and educational organization, tax exempt under the Internal Revenue Service. And your tax deduction, your contributions are tax deductible to the extent permitted by law. If any of you are interested in sponsoring a lecture, please see me. We have the goal this year of getting at least half our lectures sponsored, but since we met that goal, we're now moving on to seeing if we can get all of next year's lectures sponsored individually. So if any of you are interested, please let me know. And if you are a member and you haven't paid your dues, please do so. So our next lecture will take place at 8 p.m. here in the Powell Auditorium on December 7th. This will be the 2,400th meeting of the Society and the final lecture of the fall 2018 lecture series. Now, France Cordova, the director of NSF, had been scheduled to give this lecture, but she called me 2 days ago and said that something urgent had come up and she would not be able to make the date. So we are working to get another speaker, and I will post that to the website as soon as possible. And I'm very sorry that she's not going to be able to come and speak. So she's crossed off. On January 11th, we have the President's Lecture, which is going to be given by Lee Cronin, a chemist from the University of Glasgow, who works on a variety of subjects, including trying to create things that look like they're living from inorganic matter, and automating chemistry and using three-dimensional printing techniques to design custom chemical reactors to automate chemistry. And we'll be posting the exact topic of his lecture within the next few weeks. January 25th will be either a lecture on Venus or more likely a lecture on wearable biometric sensors. On February 8th, Raman Sundran of the University of Maryland will be coming down here to talk about supersymmetry and multidimensional spacetimes. And that lecture is sponsored by PSW member Frank Robert, who's somewhere in the audience. On February 22nd, Davy Bach of HHMI Genelia will be talking on neural mapping, and his lecture is sponsored by PSW member Tim Thomas, who's right there. And on March 8th, we have Ramesh Gopinath of IBM to talk about the legitimate uses of blockchain, of which there are many. This is not going to be a Bitcoin lecture, and you won't learn how to make a fortune in the cryptocurrency market. On March 22, we have the reciprocal of January 25th, either wearable sensors or the lectures on Venus. On April 12th, Mary Angela Lasanti of Princeton will be talking about dark matter. And that lecture is sponsored by PSW member Erica Kane. On April 26th, my friend Kim Janda from the Scripps Research Institute will be coming to talk about making vaccines that prevent people from abusing drugs. And then on March 17th, we have the annual Joseph Henry Lecture that I'm hoping will be given by a well-known figure in the robotics field. Information will be posted on all these lectures in more detail in the coming weeks. The social hour ends at 10:30, after which PSW members and guests meet at the Fairfax Hotel Lounge across the street. And if you want to join us, please speak with corresponding secretary Robin Taylor or membership director Lloyd Mitchell, or with me sometime during the social hour. Please use the side entrances to exit the building, or the side exits to exit the building. And I will now accept a motion for adjournment of the 2,399th meeting of the Society to the social hour. And Bob is ever ready with a motion, so we have a motion. Do we have a second? We have a second. All in favor? Anyone opposed? Too bad. The meeting is adjourned to the social hour.